There we go.
Welcome to another episode of Absolute Zero. I'm Bertrand Leroy.
I am Rachel Appel, and
Today we are going to talk about the center of the universe.
other than me,
Yeah.
yeah,
Another can of worms.
another can of worms. Yes.
But before we do that, I think we should follow up on some of the stuff we talked about last week.
Okay.
So we had quite a few people reacting, sometimes a little violently, actually, aggressively, should I say.
Okay.
So it seems like this is really important to a few people. I mean, flat Earth. Actually, some of the reactions were such word salads that I'm not a psychiatrist, of course, but from what I've seen and what I've Googled, it seems like this actually could be symptomatic of some mental diseases. So I definitely don't want to make fun of people who have disabilities like that. But that's not all of them. Some were actually pretty articulate and pointed me to various videos that are supposed to make their case. And sometimes also accusing me of not doing my research, which I found particularly funny because I did about 10 years of that.
So I was just thinking that.
So I think in this context, doing your research means Google it.
At a minimum.
For 5 minutes. So yeah, I watched some of those videos, and in particular one that was a so-called debate between one flat earther who was calling people who believe the Earth is not flat ballers. Apparently, that's the pejorative term in that community that is similar to Darwinist or evolutionist, that sort of thing.
Okay.
So the arguments are really weak and thin and easy to check their force. But there was another thing that struck me, which is that so there is a category of people holding those ideas who are actually very obviously lying. And apparently it's okay to lie to prove your point. And the reason why those guys are lying, in the case of that particular debate, is that they are creationists. So it's lying for Jesus, basically.
Okay.
And so that debate was interesting in that. So there was the flat earther and the round earther, and the guy defending round Earth also was a young Earth creationist.
Okay.
And being very, very, very proud of it, putting that forward as apparently some kind of qualification that was making him more credible.
Okay.
So that's okay. So there are lots of lies and quotations being taken out of context. One particular argument was about the Van Allen belt or belts that protect the Earth from radiation, and that also trap a number of particles around the Earth, making those zones quite dangerous to go through. So you have protons and electrons spinning around the Earth in those belts, and if you send a spacecraft through that, that's a pretty dangerous place to be.
Right.
Which is something that had to be solved to go to the moon, right? So they evaluated at the time the dangerosity of that. They plotted trajectories that were going through the thinnest parts of those belts, and basically taking the risk. And that went okay. And it worked. And recently, that guy from NASA made a video where he was explaining how we would send the Orion spaceship into deep space, including missions to Mars. And at some point, he says that, yeah, going through the Van Allen belt is a problem that needs to be solved. And that apparently is a trigger to say, yeah, there you go. NASA admits that it's impossible to go through the Van Allen belt. Right. Why don't they use the same capsules they used to go to the moon? And there you go. For them, it's proof that we didn't go to the moon.
Because the capsule that's built to go to the moon is built to take so much weight under such amount of time with such an amount of crew. There's all these dimensions and variables.
No,
you need something very different to go to Mars.
It is actually a play on words on the fact that this guy says that it's a problem that needs to be solved. But there are a lot of problems that need to be solved when you're going to a satellite or another another planet. You have to solve the problem of getting out of Earth's gravity. You have to solve the problem of having enough fuel. Those are all problems you need to solve over and over again every time you do it.
Well, and what do you do when Matt Damon inevitably gets stranded again?
Yes, yes. Again, that guy. I mean, come on. How many times have we had to save that guy?
So much money.
Yeah, so that's an argument that is in completely bad faith, and they just stop until they hear the little piece that they can quote out of context and reuse. So, regular tactics when you have...
that's not a very good...
when you start from the conclusion and work backwards, you tend to do that sort of shortcut. And then there are some of the most common arguments that those guys advance, which are that the blue marble kinds of photos that NASA publishes, and not just NASA. I mean, any space agency in the world who has cameras in space can take pictures of the Earth. And
that's a lie. We don't have anything in space.
That's the argument. And the argument is that the pictures to them don't look like the idea they have of it. So they have a certain idea of what a picture of Earth from space should look like, and those pictures have deviations from that idea that they have,
right? And
so they think that this is proof. So
the same thing that happens with the people who believe the moon landing was a hoax.
Yeah.
They don't understand that you could put a little piece of wire through the flag and then it'll stay erect like that. That's what they did. It's
there's a great Mythbuster episode that debunks lots of those ideas.
Yeah, that's a whole different topic.
Actually, no, it's not, because to be a flat earther, you have to also deny the moon landing. So there is
that's true, I guess. Yeah,
there is a strong intersection between the two. So yeah, I've actually stolen my daughter's globe, and
she'll come on. I needed a globe today.
Apart from the concerns that a cloud looks like a cloud, and that sort of thing, where they're complaining about the shape of the cloud, and but
they're square and in a data center. I mean.
Yeah, exactly. Okay, so there was one particular complaint that is really easy to address. Okay, so here the camera here is about the distance of a geostationary satellite. So this is the view that you get from a satellite that is rotating in sync with the rotation of the Earth, which is 36,000 kilometers. And I'm being very approximative here. So this is the kind of view you'd get from one of those satellites. Now, if you're in a lower orbit, you're going to have a much more partial view of the Earth. Mm-hmm. And see how Africa here looks a lot bigger?
Yeah.
Or North America here looks a lot bigger? And just to get it into the frame becomes more and more difficult as you get closer to the camera, because your horizon is actually getting smaller. So when you're on a sphere, when you're above a sphere at any distance, your horizon is a circle somewhere on that sphere. And the closer you are,
What this is called. There's a name for this phenomenon.
horizon.
I forget what it's called. Yeah, something like that.
And if you are actually on the surface, your horizon is at 0 meters. You are at the horizon. And the farther...
If you're on the surface looking down, but if you look out, then the horizon's out there. So like I'm standing on
the higher you get, the farther away the horizon is. If you're 2 meters tall, the horizon is at 5 kilometers, something like that, on a perfectly flat surface and with perfect visibility and so on. And then you get on a plane, and when you are on a plane, let's say 12 kilometers above the surface, which is typical for a plane flight, then your horizon is at almost 400 kilometers. And so on. But you never see half the sphere. There is always, I mean, if you're here, you certainly don't see half the sphere. But even if you're here, you don't see half. You see almost half, but you don't see half. Your horizon is still not taking the full circumference of the sphere. And then there is the problem of actually getting that into the field of view. And here I have a wide angle lens that makes it very visible. And here, see how you still see a sphere, but it's distorted. Okay?
Yep.
And that's the second point, which is, so they're making the point that the photos that are supposed to show you the curvature of the Earth actually show you the distortion from the camera.
Right, because it does not have that wide angle in front of it necessarily.
Yes, and they have a point, because as you know, you cannot project a sphere onto a plane without distortion. You have to have distortion globally. I mean, you can have local areas that are almost distortion-free, but as soon as you're projecting a sphere on a plane, you get distortion. Your straight lines are actually not straight. If you look at this line here in the ceiling and put a ruler on that, it won't be straight or everywhere. So there is distortion. So you cannot use a photograph to say, see, here is the curvature of the Earth. This is not how it works. The way you do it is that you show the whole thing. But you know, when you show a picture, for example, from a plane showing the horizon, well, that's not making a good point in one way or the other.
Right.
What does make a point in the way of a curved surface is when you see a boat going over the horizon.
If it just goes bloop,
yeah,
like that, you may be onto something.
But wait.
Either there's a waterfall out in the middle of the ocean, or
yeah, well, so it goes it goes below the horizon somehow. But...
And if it makes the bloop sound,
yeah,
even more to investigate.
So you know what the argument against that is?
Against the ship going over like that it doesn't?
I've seen boats that were pretty far away that I could see entirely. Yeah, you're above the water. So if the boat is close enough, if it's not more than 5 kilometers or so, you won't see it start disappearing. And if the boat is let's say 10 meters tall, then it will need to itself be your horizon needs to be farther than its horizon. So you need to add both distances, and then you need it to be 15, 20 kilometers away before it completely disappears.
You know, this brings up a whole thing in that you think about this is all about looking at things from a different perception to get to the truth.
Mm-hmm.
Right? These, different ways of being able to see things, and just, people looking at one tiny detail and missing out on a whole lot of other information.
Yeah, and there is a lot of cherry picking of information here, a lot. And rejecting all the information that contradicts what you think, and accepting blindly all the information that goes in the direction you want. It's very, very manifest. Yeah, so there is also the fact that you need a lot of people to lie for something like that
For
to.
conspiracy.
I mean, it's just it. So you have, on the one hand, cherry picking of information and having to discard pretty much all of physics, and those guys actually do. Some of the comments we had were actually claiming that gravitation doesn't exist.
It's just a theory.
Yeah, that is, it's actually some electromagnetic phenomena, and this is where the word salad usually begins.
Yeah. Oh, that one that you showed me. Yeah.
Yeah.
That was just kind of unintelligible.
Yeah. Well,
You know, I was thinking.
I understand all the words in those sentences.
It's just that they don't make any sense
No.
when you just throw them together and toss them. Yeah. So if you look at, there's so many different scientific fields. Like look at even plate tectonics. Kind
Yeah,
of backs up around Earth, being that plates shift over the mantle and the crust, and you need that to be kind of spherical. Stuff like that. You need the tides to work the way they do. Seismology, even some of evolution, right? Some parts of that would tie in. Astronomy, physics, cosmology. I mean, look at all these entire areas of research. You're talking about millions and millions of people over, hundreds of years of accumulated knowledge.
And they would all have to be diluted in exactly the same way.
In exactly the same way, and none of these people would want to expose or be a whistleblower, like not any of
so
millions.
We do have examples of millions of people being diluted in the same direction, right? We do.
Well, that does happen, yes.
The difference is that if you have any understanding of science, you know how it's a process or a set of processes that aim exactly at the opposite of that. And those of us who are trained in science have been trained in eliminating bias and preconceptions. It's the whole point of science. So you would have to train those millions of people in recognizing falsehood, and then fool those people nonetheless. It doesn't make any sense.
Yeah, or get them all on board with lying, and that's just it's just too much of an endeavor. What happened to Occam's razor, right?
Yeah, flat Earth basically requires that you throw away all of science, everything. Yeah, doesn't work. Geocentrism. Okay, so of course, they also believe that the Earth is the center of the universe.
Oh, sure.
There's
the flat Earth.
Yeah.
Right? The flat Earth, and it's the center, and the sun goes around.
Oh, you're silly. It's a disk.
Little ships just boop off. Look, you get to literally here. You get to the end of the Americas.
Oh,
right.
Okay.
And then
wait.
You fall off the Earth.
Yeah.
Because America,
One more about flat Earth. Going around around Antarctica.
Who wants to do that?
Well, lots of people actually have done that. And,
yeah, I know, but it's so cold down there.
And well, I think we would have noticed if you needed to travel such a distance to go around Antarctica that would be inconsistent with what you see on a globe.
Right.
Yeah, that's just one more. That is just and that guy from that video, he actually says, well, yeah, that is a problem.
You think?
You bet it is. Okay, well, so geocentrism, I think, is interesting because it's one of those where you can say, yeah, well, no, of course, silly. The everything is not rotating around the Earth. Everything is rotating around the sun.
Yeah, but if you're just all right, any kid who was to just go out and play all day in the yard and see the sun trekking across, and then in the evening maybe see the moon trekking across, it's going to look to the casual observer like we are at the center of at least something where the Earth gets up and or the sun rather gets up and circles the
it's
Earth.
a very natural thing to
And
believe.
if you look at some of the ancient texts that are out there, including some of the holy texts, and it talks about the sun rising and setting, that's where we get some of our language around that from. Plus, it kind of looks that way. So even the Quran kind of didn't even know what to do with it. So they said the sun sets in a mud puddle. Creative. I like that. Fun comparative to some of the other.
Yeah. 3 points for Slytherin.
It's out there, yeah.
Yeah, so I think this one is interesting because it's a good way to introduce the idea of relativity, where movement is relative, and it in a large way it's a matter of which referential, which system of coordinates is the more convenient to what you're trying to do. And there are actually lots of domains where you would be silly to not use the center of the Earth as the center of your referential.
Right.
And even more locally, in most physics experiments, you're going to take a referential that has its center in the middle of your lab. That doesn't make your lab the center of the universe, of course.
Right. That's just your starting
but
point.
it's just that it's the system of coordinates that is the easiest to use for what you're doing, and you can afford to ignore all the little imperfections resulting from it not being a referential that is just traveling in a uniform way through space. Right?
Sci-fi fans know this concept because you have a lot of center points in different films and whatnot.
And if you're studying the trajectories of planets in the solar system, then you should probably take the sun as the center of your coordinate system. And if you're studying the movement of the galaxy, then the center of the galaxy is the right spot to consider, and so on and so forth. The point being that there is no center in the universe. There is no center to the universe. So any point is equivalent to another. What is trickier is rotation. When you look at when you look at two referentials, one moving in a uniform way with regard to the other, there is no difference. The equations of physics are the same, right? Now, if you take two systems of coordinates, one of which is rotating, then the laws of physics have to be transformed, right?
So the Earth does that.
Yeah.
Right, and then the moon mostly just kind of stays facing us and kind of goes like that.
Yeah, and that would be
rather than actually rotating around us, rotating around the sun.
Yeah, that would be a good topic to look at another time. So that's a problem, the fact that rotating referentials are not equivalent, which means that there is a privileged there is something you can say that the referential is turning by looking at those inertial forces that appear in rotating referentials, which means that there are sets of coordinates that are privileged relative to others, and this is a problem that troubled Mach. It's called the Mach problem. The idea being that if you had a completely empty universe with just a bucket of water, and you made that bucket of water rotate,
okay,
then the water would be, well, assuming that you had gravity, you still had downwards gravity. Let's imagine we're in a flat Earth universe.
Okay.
So the water, well, if it's just a blob of water, you would have a sphere that would get distorted by the rotation, right? Which shows that all the directions are not, well, all the rotations are not equivalent. And this is a problem that really troubled him, because otherwise there is nothing in the universe that fixes those directions. There are no objects that tell you this direction is not the same as this one. See what I mean? The symmetries of the problem, there is something troubling with that.
Right.
And it's those considerations that actually give rise to general relativity. It's consideration of that sort. What is the nature of movement, and how do forces appear? What are forces of inertia? All those considerations that are very, very theoretical constrain the laws of movement and how you go from one referential to another. And just from those very abstract considerations, you can extract general relativity, which is very, very interesting in itself.
Yes.
So all that to say that the Earth is not the most convenient coordinate center if you're studying the movement of the planets, as many observers and scientists have observed before it was all sorted out by the likes of Kepler and Isaac Newton and so on.
Yeah.
So moving the center to the center of the sun is a pretty efficient move that simplified everything. So when you have a set of equations that is very complex and needs stuff like epicycles and epicycles and epicycles, and you can replace that with one single elegant equation, then you know that you've done some pretty awesome science.
Yeah, something like O equals mc squared would be awesome.
Yeah. So just one more thing, which is that even if you consider the Earth rotating around the sun and exclude the rest of the universe, the center of that system, well, the point that is the most convenient to consider the movement of the system is not the center of the sun, it's the center of mass of the whole system, which is somewhere off the center of the sun.
Right.
Just specifying that because people like to nitpick. All right.
Okay.
And
there was actually one more thing. I don't
yes.
know how it fits in exactly, though, but I read this somewhere that as the moon actually does rotate around the Earth, that it pulls on it just enough that it creates a tiny, like, little bulge in the Earth that kind of almost follows it around. Almost when you're talking about the sphere of water in space and how it bulges out, and that the Earth does that just a tiny little bit. And I was like, oh, that's interesting.
And so one of the ways I like to explain why the moon is always facing the Earth. So it's locked in position.
Yeah.
It's gravitationally locked with the Earth. Well, and there are several ways you can
a dark side to sing about.
Mm-hmm.
So Pink Floyd had a dark side to sing about. I mean,
yeah, absolutely. Well, it's not dark. It's the far side of the moon. It's just lit by the sun the same way the other side is. Yeah, so that's really interesting because there are different ways you can understand why this is, and all similar systems eventually will get gravitationally locked that way if you wait long enough. The reason why it happens can be explained in several ways, one of which is the following. If the moon was rotating like that, so you would have those tides in the rock that are small, but that still exist. And the thing with the tide is that it moves, right? So you have this deformation that is not always in the same place, which means that you're going to use energy.
Yeah.
Moving that deformation. That energy comes from the gravitational energy of the system as a whole. And it goes into the deformation. And then it's lost into heat and so on. But the point is that the stable state for the system is when it stops moving, when it is gravitationally locked.
Okay.
And at this point, you are not spending any energy in deformation any longer, because the deformation is always in the same spot. So, as we know, physical systems naturally decay into their stable states. So because that state is more stable, this is where the system evolves naturally. Then you can start to make the calculations and figure out how long it takes and so on. But essentially, that's the gist of it, if you want to understand just why that is. It's not a coincidence. And we're out of time. Cool.
Yep. I think that's it.
Yeah. So this has been another episode of Absolute Zero. I'm Bertrand Leroy.
I'm Rachel Dell.
And we'll see all you lovely people next week, if we are there, or another week otherwise. Bye, everyone.